Whoops. Okay, I'm recording now. So one thing, again, I think something happened, or you might not have done the reaction rate labs yet. It doesn't matter if you did it or not. But this is a huge wink, wink section of my PowerPoints. You in your labs on your tests, test number 2, final exam. Wink, wink, wink. I might ask you how to make a chemical reaction faster. Now, we did this on Thursday, and I didn't have a big attendance on Thursday, but if any of you guys have any questions on this, or you can go look at the videos. I don't know if Thursday's video is uploaded yet, but it will be. So I'm just very quickly going to go through this, the ways to increase a reaction rate. First thing, make it hotter, increase the temperature. This doesn't always work, but for most chemical reactions, if you increase the temperature, the particles are moving faster, there's more collisions, they're going to break bonds and form new chemicals. So that's the first way. The other way, and again, I'm going a little quick through this because I did this on Thursday, we increase concentration. This has a similar result of increasing temperature. It's all about collisions. But increasing concentration, it doesn't increase the speed, but it does increase the probability, the chance that two molecules will bump into each other. And I think on Thursday, I linked this to driving. And increasing temperature is like driving really, really fast. Increasing concentration is like when there's rush hour traffic. So, everybody's driving home from work. When people drive fast or the roads are busy, there are more collisions. So more temperature, more concentration, more collisions. This next one is technically concentration. It's concentration in disguise. When you're dealing with gases, you can compress them. You compress them by increasing the pressure. More pressure means less volume. Remember that from chemistry 1120? And if there's less volume, there's less room for the particles to move, which means they're going to collide more. And I used to always see this when I lived in Alsad. I would always take the expressway or D-ring or whatever you call it home from work. And when you're driving from Festival City towards Landmark Mall on D-ring, and up by Festival City, it's like 5 or 6 lanes, and it's different now. I mean, the roads are all changed, but years ago there was like 5 lanes, and then it turned into like 3. That's like increasing pressure. You're forcing all of these cars to squeeze into 3 lanes, and again, that's commonly where you would see a collision. So you can kind of think of reactions like increasing reaction rate. Sorry, you can kind of think of car accidents or driving like increasing reaction rate. High speed, high concentration of cars, narrow roads, there's going to be crashes. This is one you might hear about in your lab, but this is certainly one that anybody who drinks coffee or tea would know. Typically, powders react faster than like large crystal solids. And this has to do with surface area. Now, what does that have to do with coffee or tea? Sorry. I don't know how much coffee or tea you guys drink, and I don't know how you add sugar to it, but in some places in the world, they use cubes of sugar, so a cube like this, right? Other places, and this is what you typically see, at Starbucks and stuff, they use powdered sugar. This is going to be faster. It does now. Dissolving isn't necessarily a chemical reaction, but with powdered reactants, there's more surface area. The molecules can touch each other. And really, that's what a collision is. That's what reaction rate is. The molecules have to touch. So yeah, if you can figure out a way to get more molecules to touch, it will make it happen faster. And finally, this is where we ended on Thursday. And I didn't really have enough time to get into this, but there's another really cool way to make a reaction happen faster. And you might see this in your, you should see this in your lab, your reaction rates lab. Again, I don't know if you've had it yet, but you will see either Michelle or your instructor will show you this, or you'll physically do it yourself. But there are ways to make reactions faster by adding something called a catalyst. This is typically a test question as well. All right, so first of all, let me just check the chat here. Ooh, I got some good questions. Okay, so 2 questions. And the first one from Aman is actually relevant to this slide, so I'm glad I waited a minute to open the messages. HCl can actually be a catalyst. You saw that in your organic chemistry polymer lab, where you would add a concentrated acid for the esterification reaction. I don't know how it fits into like the engineering term of catalyst like we're going to talk about today, but what the HCl does is it helps the reaction go faster. So you can kind of think of that like a catalyst. In engineering, a lot of catalysts are actually metals like platinum. You see them in cars in what's called a catalytic converter, and they give the reaction a way to happen faster without using up that catalyst. Somebody the other day mentioned enzymes in your body. These are chemicals that help your body do things, but they don't get used up. And I'll talk a little bit more about that in 1 minute. And Harold has a good question. Yeah, so Harold, you're talking about like solvents and saturation. This concept of solids reacting faster is kind of like when you mix 2 solids together. When you're putting these things in solution, it gets a little bit more complicated, and that's when you would look at concentration. So this powder thing typically only refers to solids. All right, so catalyst. What are catalysts? And first definition, definitely one you need to know. This is an extra chemical that's not used in the overall reaction. It helps the reaction, but it's not a reactant or product like you think when you think of a chemical reaction. So it's like a helping hand, but it doesn't get used up. So how does it make it faster if it's not getting used up? Well, what it's doing is it's giving the chemical reaction basically a shortcut. It's allowing the reaction to go faster by lowering the activation energy. I mentioned this the other day. This is like driving around Qatar and, you take a shortcut. So, if I wanted to leave CNAQ and go to West Bay, I probably wouldn't turn up by Festival City, go down D-Ring, connect, I mean, that would be a long way. The lower a catalyst is the fastest route. So it's like a shortcut when you're driving. And typically, because catalysts are extra chemicals that don't get used up, you can typically reuse them. Okay, I would know at least the first 2. So wink, 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 if you were ever asked to explain a catalyst, it's a chemical that's not used in the overall reaction, and it makes it faster by lowering activation energy. And I have a beautiful picture here. Oh, I might have a video. I don't know if this is going to play. Nope. Let me just try one more thing. Here we go. Here we go. I typically don't like to play videos over Zoom, but I will in this case because it's really short. We won't get into the chemicals. This is hydrogen peroxide and manganese dioxide or manganese 4 oxide. And you can see the minute they added the hydrogen peroxide, it went a lot faster. Sorry, I didn't mean to do that. Let me go back. Okay, so there's the reaction going, and they're going to add a catalyst. boop, and it goes way faster. You can see like the puff of smoke or whatever. You'll do something like this in the lab, but a little bit safer. It's a little difficult to get concentrated hydrogen peroxide in this country for like safety reasons. It's used as like an accelerant or an explosive, but you'll do something like this in the lab. Sorry, it's not the best video and it's hard to do it over Zoom, but you get the idea. All right, let me check the chat. Yeah, I like my traffic metaphors because it always helped me understand this, and especially like where I'm from in Canada, there's no traffic. We have one street light basically. So I'm from a pretty small town. There's no expressways and overpasses and stuff. There's only 20,000 people, not 3 million like in this country. So anyways, when I came here and I started seeing traffic and roundabouts and it's really made a lot of sense. So here is, and this is another kind of wink wink thing. Boop. I'm technologically challenged here today. There we go. This is typically a graph that we did this in chapter 2. You had this on your test the other day, but you might in chapter 3 have to sketch what a catalyst would do. And I don't really need to see the 2 bumps, but what a catalyst would do is it would just simply lower the activation energy. Oh, I guess that's not right. So the EA, and again, you can think about driving. I know Abdul like my traffic references. Imagine if you were riding a bicycle or driving up a very steep hill in Europe. Which hill would be faster, right? Going up this purple one or going up this little smaller red one? Obviously, the smaller hill, you would be able to bicycle up or drive up a lot faster. So there you go. So some examples, as I think it was Aaron or somebody the other day mentioned enzymes in industry. So in engineering, you see platinum a lot, palladium or platinum. And then in esterification, we used acid, and Iman mentioned that. We did that in lab 1. Now, this is, aluminosilicates, they can break down big hydrocarbons as well. So platinum and aluminosilicates. Don't worry, you don't need to memorize aluminosilicates. But there's lots of different chemicals that make a reaction go faster. Okay. Now, there's one slide here I'm going to cover, but I just want to give you a hint about a question you might see in a lab or on a test. If somebody asked you, why would you use a catalyst, or why would you make a reaction happen faster? Like in this concept check, why would we even want to make concrete harden faster? Well, there's an old saying. I know in the West, we use it all the time. The saying is, time is money. So imagine if you're trying to do a chemical reaction for an industrial process, okay? So you're at a giant refinery or you're making polymers, and you could use a chemical like a catalyst to make the reaction happen 10 times faster. And that catalyst gets reused. You don't even have to keep buying it. You can use it over and over. Well, that means you're going to need less time, less people. You're going to spend less money, because if it takes you, you have to pay someone 2 days to make a chemical or 2 hours, I mean, it's less money. So I haven't taught your labs in a while, but there was always a lab question of why would you use a catalyst, or why would you even want to make a chemical reaction faster? It saves time, and saving time can save money. So concrete formation. Concrete is kind of like a mixture of, like, when they make concrete, they take kind of like this powder, mix it with liquid, pour it out, and it hardens. But you want that to happen really fast, because you don't, for example, you don't want animals or birds or people walking through the sidewalk and ruining the pavement or the concrete. In the Middle East here, there's a lot of concrete buildings. You want them to set very fast so that there's no breaking or cracking or bending. It's really good to make concrete harden fast. So ways you could do this is you could increase the temperature, so you could use warm water. You could make sure the chemicals, the concrete powder that you're using is powdered and not in chunks. So again, I don't know if you've ever seen anybody make concrete, but they typically take a powder chemical and mix it with a liquid. You could increase the concentration of the reactants. So have highly concentration of that concrete powder. You could use a catalyst to help you do that. And that's called, in usually concrete formation, they call it an accelerator. And a retarder is the opposite. So retarder technically means to slow something down. Like in French, retarder means to slow something down. And sometimes maybe you want a process to be slower so that there's less imperfections, for example. I won't get into that because that's beyond my scope of chemistry. But I know in lots of arts and crafts and, different processes, sometimes fast isn't good because if something hardens really fast, you might have air bubbles trapped inside. It could, fracture through stress. So sometimes speed isn't always the best, but typically, yeah, you'd want a reaction to happen as fast as possible. Whew. Yeah, so Aman, you kind of covered that. There's, some things you want to happen slowly so there's less mistakes. But again, this really is a complicated question because it depends on what you're making. Personally, you would want concrete to harden very fast to prevent things. I know, for the easiest example I can think of is when people pour concrete for sidewalks. Or for roads. You don't want it to take 3 days to harden because, people can't use it. So yeah, it kind of depends on what you're doing. I know, again, in the art industry, creating fine crafts, you typically make the process go slow. But if you were creating a polymer and you wanted to go fast, you could use a catalyst. All right, that took me way longer than I thought, but that's okay. That's cool. So I know it's late. You guys had a long week last week. You had tests and midterms. I'm just going to get into the next section. And then that'll be it for today. So let me open the next section here. We won't do all of this, don't worry. I'll just kind of introduce this. Now, I'm laughing because for all of my folks in this course who like math, math is coming back just for this section, really. Unit 3 is really interesting. Unit 2 was a lot of math. Unit 3 is about a 50-50 mixture. So there's some theory, but there is some math. So we're going to look at some things here like a rate law, a rate constant. This can sound really confusing. It's really not, especially at the level we do it in this course. It's not that difficult. And then we'll look at half-life, which some of you might have heard about if you've done a biology course, or even I should say physics. You might talk about the half-life of isotopes. So this is math, but once we finish this section, we're back to no more math. All right, cool. Hold on, guys. I'm going to do something. I'm going to save this and close it. I think I figured out why I can't write on my slides sometimes. It's when I download them from D2L. Let's see. Yeah, okay, I figured it out. Woo! When I download them directly from D2L, I can't write on them until I save them to my computer. So there we go. All right, get ready. Just give me maybe 5 minutes, 10 minutes maximum. I just want to introduce this, but this is going to look a little crazy, but it's actually pretty easy. In my opinion, this is definitely easier than calorimeters. All right, a rate law. This is an equation that shows how the rate of a reaction is related to the concentration of reactants. Now, remember, the rate is the speed a chemical reaction happens.
Sir, we can't see your screen.
You can't see my screen? Okay, sorry. Give me 1 second. Thank you for letting me know. Here we go. Sorry. So let me just go back 1 second. I just wrote the word math here. This is a very math heavy unit, or section of a unit. Okay, so like I just said, the rate is the speed of the chemical reaction. When we're looking at the speed of a chemical reaction, we don't care about the products. Now, this is very important that you only consider this for rate law. Okay, we're going to do something a little later in this chapter called equilibrium constant, and that's completely different. So a rate law is about the speed of a reaction going forward, and we only care about the concentration of reactants. So this is my rate law for this equation. Now, what is going on? Where did this come from? And this is probably what we'll look into a little bit more on Tuesday. What does R mean? What does K mean? What are these square brackets, and what are the 2 and the 0? Where did these come from? Right? It's easier than it sounds, I promise you. So let me erase my writing here. K is called the rate constant. It's like pi or gravity, or maybe a better example is it's like specific heat capacity. What we learned in Unit 2 is that the specific heat capacity depends on the chemical. We typically picked water, but it could be for lead, for iron, for nickel. Rate constant is unique. This is obviously something that is given to you. These numbers, by the way, come from gigantic data books. So what are these numbers? Well, the numbers are called your reaction order. Okay, so this is called your order. I don't know why that's not written on the slide. Okay, now this is where it can get complicated. Don't worry, I'm going to take my time. We'll look at this in greater detail on Tuesday. But reaction order explain how each of the reactants actually react or relate to the rate. So this 2 we would call second order, pretty easy. Okay, so this 2 here that I'm circling, this would be called a second order reactant. And what that means mathematically, and again, we don't really need to get into this in 1121, but if you're curious, what it means is if I doubled the concentration, I would well, I'm confusing myself, but if I change the concentration, I would change the rate by a factor of 2 or an exponent of 2. So the word in English would be doubly. So actually what would happen is if I doubled the concentration, I would quadruple the rate. And again, we're going to talk about this more on Tuesday if you're all confused. I think after your midterm week, you should take a little mental break, and we can worry about this a little more on Tuesday. Okay, so what about that 0? Well, if you guys are good at your math, if you take any number, a million, a billion, a trillion, and you raise it to the power of 0. You can do this on your phone or your calculator right now. It always equals 1. So a 0 order reaction, think about what the number 0 means. It means nothing. A 0 order reaction or 0 order chemical does not affect the rate at all. And we're really only going to look at 3 types of orders. There will be first order, second order, and third order. 0 order, first order, and second order. So here's another example. And guys, again, do not get overwhelmed with these examples. We're going to practice this more on Tuesday, I promise you. But this is our rate law for this particular reaction. Now, you'll notice here, there's no number. And I shouldn't have done that. Let me get my highlighter. There's nothing. So think about math. When there's nothing in front of an x, or there's nothing written as an exponent, you guys know that that's technically a 1. So this would be called first order, or a first order type of chemical. All right, so he's first order. So now what's going on with the Fe? How come Fe isn't written there? Well, Fe must be a zero order reactant, because when you have something that's zero order, you don't even need to put it in. Again, I will explain all of this in greater detail on Tuesday. This sounds crazy, but it's really not. Oh, and Abdul Halim, I hope I answered your question. Maybe not, but the 2 and the 0 are what's called the order. These numbers, you guys, will be given to you. So like a lot of this stuff here, if you're feeling confused, a lot of these numbers, you like a normal person, like a actual scientist would look it up in a big giant book. None of us are actual, well, not yet. You guys will be scientists hopefully someday. I'm just a teacher. I don't do many experiments anymore like I used to, but as students, you guys would typically be given this. It would be in the question or in the data booklet. But out in the field, or if you were doing a crazy university research project, you might look this up in a gigantic textbook. I have one of them in my office. It's like 1,000 pages, and it has all of this information in there. All right. Okay. Sorry, I just want to do. Okay, let's do 2 slides and we're done. And this might make you feel a little bit better about this. And again, I cannot stress this enough. If you do not feel good about this now, just wait till Tuesday, because we're going to practice this. But 2 more slides, and this might make you feel a little better. So I'm telling you about what's called the order of the reactants, right? Each reactant has a different order. So what if, wink, 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 like a multiple choice question was asked, where I said, what is the overall order of this reaction? Overall, meaning of all of the chemicals. Well, this is easy. To find the overall order of a reaction, you just add the exponents. Done. Now, this is where it gets confusing to students, because you have a lot to study. You're going to have, tests and papers and things to be doing. I see a lot of students forget this, and they try to multiply them, or they try to do these crazy calculations. Nope. The overall order is by adding the exponents. So let me get my highlighter here. I would add the 2 and the 0. So one of my chemicals is to the second order. One of my chemicals is 0 order, which means this doesn't really count. This is second order overall. Now, what about the second one? The second one doesn't have any numbers written, but we know if there's no numbers written in mathematics, it's always a 1. Right? So these have little secret hidden 1s there. So we got 1 and 1. Well, if one chemical is first order, the other chemical is first order, it's overall second order. And then in the last one, this is the easiest one, because we don't even have to do anything with this one. Again, there's no number here. But because there's no number, it means that it's not a 0, it's not a 2, it's not a 3. In math, when you don't put a number there, it's a 1. So this is just first order. Easy. No adding, or no adding for the last one, no multiplying, nothing like that. So you might see this as like a part B for a question, or a multiple choice, where we give you a chemical reaction, and I just say, what's the overall? And I'll give you the reaction. I'll give you the rate law. And there you go. And Iman, so 2 questions. Would it be wrong if you started with the second molecule? Nope, not at all. Because if you add numbers in any order, you'll get the same result. It's not like dividing. So it doesn't matter if you added 0 to 2 or 2 to 0, no problem. And the other question is, would I like to be a scientist? And I don't know. I've thought about that a lot. When I was in university, when I finished chemistry degree, I could have went further with chemistry, or I could have did teaching. And I don't know. I don't know if it was for me. I don't know if I'd want to be in a lab every day doing research. Maybe someday, who knows? But I like teaching for now. It's definitely different, but fun. And I'll tell you, It was a lot easier than doing my master's in chemistry. That would have been crazy. Hadil asks a good question, and I think it's just like a bullet. What I mean by that is, hold on. Hadil's question's really good. What does the negative mean? Sorry, that's just meant to be like a bullet, if you were making a PowerPoint. So it's not a negative, it's like a bullet point. Sorry about that. I could totally see why that's confusing. All right, well, this is it, the finale. And I'm really showing you this slide so you'll feel better about this, because this is how easy it is. This is a totally fair game test question. Now remember, I have to give you this information. So if you know the order of the reactants, you can write the rate law. And I have to give this to you. So rate laws are always composed, and this is kind of the weird part about this, is rate laws are always composed of the word rate, or R. I typically used to write the word rate, but you could just say R. It's always times K, and then it's always multiplied by the concentration of the reactants. I do not, let me start over too, but I don't care about the number 2, and I do not care about the products. So let me just start over. Every rate law is written the same. It's rate equals K. You have to have K there. It's like specific heat capacity. It's a number, again, I will give you. And then you multiply that by my reactants, HBr and CaOH2. Now, some of you, well, I'm not done. I'm very close to being done. Some of you might be wondering, why am I putting square brackets there? Square brackets means concentration. Moles per liter. Okay, I'm not going to go too crazy about if you use square brackets or round brackets. Like, I mean, it is a big deal, but maybe not so much of a big deal in chemistry, or in 1121, sorry. All right, so the next question, I think Abdul Halim, you have everything perfect. You're missing the 2 on the calcium hydroxide, but that's not a big deal for now. And Aman mentions, why don't we care about the balancing of the numbers? That has nothing to do with the rate. Balancing of numbers is for the law of conservation of atoms. It's for what we would call stoichiometry. But for rates, it doesn't matter. Okay, it's the same. You could have a 5 in front of this. It does not affect the rate. Again, the balancing is just for law of conservation of atoms. All right, I'm almost done. I mean, I guess I technically am done, but let's read the example fully. In the reaction below, HBr is first order, and CaOH2 is also first order. Okay, well, I'm good. I'm done. Now, there's 2 ways you could do this. You could leave it like it is, but you know what? It wouldn't hurt if you guys, felt more comfortable. You could put a 1 there. I don't care. I typically, when I teach this in class and I'm writing on the board, I will typically put the 1s in there. Okay, so that's A. I'm done. That's my rate law. Again, guys, we are going to practice this tomorrow, I promise. B, what is the overall reaction order? Well, 1 plus 1 equals 2. It's second order. That's it. That's a test question. I think I have another example Yeah, I got a couple more examples. I have a few more examples. We'll obviously save that for Tuesday afternoon. All right, but that's it. Again, if you guys are not liking this or feeling like, uh-oh, I miss units 1 or unit 2, don't worry. This is a little bit easier. We just need to practice it a little bit more. So on Tuesday, we will go over some more examples. All right, guys, so that's it from me. Just a reminder, tomorrow afternoon, I won't be on campus in the morning, but tomorrow afternoon I have a lab, so I'll put your tests outside my office. If anybody came in late or just needs a reminder, my office is 7242A. Okay, and you can keep those tests. You can use them for studying. I don't want them, so don't leave them. Take them, please. You could, wink, wink, wink. You might see some of those questions again on your final. So that's it for me. Any questions, let me know. Other than that, I'm done.